Good morning, everyone. This is Shireen Elhabian, and I'll be presenting to you my recent work with Whitaker in learning generative shape models directly from silhouettes. Silhouettes is a single color image of an object with its edges matching its outlines. Silhouettes can be considered as a grid structured representation of a shape where humans can recognize objects from silhouettes. So for this silhouette image, you can see, or your brain can recognize that there is a gentleman giving a woman a rose. But why humans can recognize objects from their silhouettes? Well, the premise here is that different objects from the same class attain clear differences with respect to their shapes. However, they share typical characteristics that stems from the underlying generative process involved in their formation. This premise motivates learning probability distribution patterns from shape population by modeling the distribution from an IID samples. A strong shape model should balance the trade-off between three requirements: realism, generalization, and robustness. In particular, a shape model needs to generate samples that look realistic. It needs also to generate samples that go beyond the training data while being able to model or handle unbiased noise. Strong shape models can benefit various applications that would use shapes to augment other sources of information to solve a specific inverse or forward problem. However, learning variations in the silhouette space is challenging. Binary variables entail non-Gaussian data likelihoods, which leads to intractability. High-dimensional shape spaces with limited number of training samples increase the tendency to overfit. As well, the hyperparameters associated with model complexity often result in computationally expensive discrete searches. To handle non-Gaussian data likelihoods, most existing approaches perform dimensionality reduction or non-parametric density estimates by representing shapes in an implicit function space. Nonetheless, these approaches fail to define a proper generative model, and they rely on a maximum likelihood estimate of the model parameters. Recently, stochastic neural nets have been adopted to learn distributions over binary inputs without relying on any intermediate representation of a shape. Nonetheless, these networks do not learn a specific generative process, which requires an exponential number of hidden units as well as training samples to approximate arbitrary binary inputs. In this paper, we address the problem of modeling population of silhouettes by learning generative model of a shape population directly in the silhouette space without relying on any intermediate representation. We propose a Bayesian treatment of a latent variable model. We call it ShapeOdds as a low-dimensional shape-generating process. It automatically estimates model hyperparameters via closed-form re-estimation expressions without the need for discrete searches or cross-validation. To increase the robustness of the estimated posterior, we deploy a robust function of the marginal bound that's more forgiving of the outlying pixels without explicitly knowing what is the spatial support of the outlying region. For comparison, we consider different existing approaches, including the state-of-art shape Boltzmann machine, as well as PCA on intermediate shape representations. For realism, ShapeOdds can generate crisp parameter maps with significant shape variability while preserving shape details. For generalization, ShapeOdds can generalize to unseen examples in non-trivial ways. ShapeOdds can also recover realistic-looking shapes from corrupted ones as compared to other baseline models. For more information about the formulation as well as the results, please visit our poster. Thank you for your attention.